Hello everyone, welcome to Asian Academy's YouTube channel. In this session, we'll be discussing questions related to your score booster series for the subject Steel Structures of Civil Engineering. The weightage of steel structures in GATE examination is quite less. Again, if you are a student who has been preparing for all the subjects of civil engineering, aiming for higher number of marks, then it can be a bit helpful for you. Moreover, if you are a student who is ignoring some subjects, so steel structures part you can obviously ignore because the weightage is quite less. 1 or 2 questions at max are asked. For the last 3 years, only 1 questions per session has been asked. Moreover, if you are a student who has been preparing for engineering services also parallelly, then okay, it is quite good for you because again, steel structures weightage in all other subjects is very high. When we talk about prelims also of engineering services, the weightage is quite good. So again, it's up to you if you are willing to go for steel structures or not. And here MSQ and NAT questions we'll be discussing mostly. So let's see this first question over here. Factor of safety adopted by IS 800 while arriving at permissible stress in axial compression is. So permissible stress in axial compression as per IS 800, it is 0.6 times Fy, which gives you a factor of safety value Fy divided by 0.6 times Fy, right? You can just consider this table over here and you can just directly remember what are the considerations with respect to that. Direct tension and compression 0.6 times Fy. Factor of safety over here will be equal to 1.67. When bending tension and compression are there, permissible stress is 0.67 times Fy, factor of safety will be 1.5. And when we talk about maximum shear, here 0.45 times Fy is your permissible stress and factor of safety is 2.22 over here, and average shear when we consider over here as 0.4 times Fy, it is 2.5 as a factor of safety. So you can remember this particular table for your basic questions which are asked in this. And next, when we talk about, so which of the following statements are true with respect to prying forces? So prying force is generally considered in flexible tension connections. It is an additional force which is induced in the connection because of the flexibility, right, of the connection. So when we consider a tension connection like a hanger connection over here, let's say a simple diagram, if I consider, partially it will be distributed. The main member is subjected to T and T over here. So T by 2 and T by 2 shall be considered right over here. And flexibility of the connection will lead towards this kind of a problem, right? And this T by 2 and T by 2, because of the reaction force from the corners here, there will be a reaction force which will be induced because the corners will move into the gusset plate over there. So for super imposing this and with respect to keeping in view the static equilibrium conditions, this Q force has to be added on both the sides, right? So this Q force in the opposite direction will be transferred to the connection. So it will be an addition to the already existing force due to the external loading, right? So it is a tensile force due to the flexibility of the connected parts. So option B over here is correct and should be considered in addition to the force in connection due to the external force as well. Option C is also correct over here, right? So B and C are correct in this particular case. So answer is B and C. Let's see this particular numerical question over here. A 12 mm thick plate is connected to two 8 mm plates on either side through a 16 mm diameter, and there is a power driven field rivet, right? And for that power driven field rivet, they have given the permissible shear stress value and permissible bearing stress value 90 MPa and 270 MPa in the rivet. You are supposed to find out the rivet value in the joint. Okay, and it's quite easy. We can just directly move on to the consideration. So if you see this particular diagram over here, the rivet is subjected to two shear planes, right? So consecutively, you can find out the value of the shear strength of the bolt as well. So number of shear planes are 2 multiplied by the permissible shear stress, and you'll multiply the shear area. Now here in the rivets, you will be considering rivet hole diameter. So pi by 4 into d naught square. So this will give you 2 into permissible shear stress is 90. It is given in the question. Pi by 4 into, and what is the diameter? Diameter is given to us as 16 mm. And in case of rivets, if the diameter is less than 25 mm as per IS 800, then you have to add how much? 16 plus 1.5 mm, right? It is not a bolt, it is a rivet. In case of bolt, for bolt hole considerations, the criteria is different. In that case, I would have added 2 mm for bolts, right? But in case of rivets, it will be 1.5 as it is less than 25 mm. Now over here, it is how much? 17.5. So 17.5 square. And when you will solve this, you'll get an answer 2 into 90 into pi divided by 4 into 17.5 square divided by 1000. This will give you as 43.29 kilonewton. Now this is 43.29 kilonewton, and consecutively you can find out PB as well. Now PB will be your permissible bearing stress multiplied by d naught into T. This is your contact area. Permissible bearing stress they have given to us as 270. So 270, take the value and multiply this by d naught, that is 17.5, and d will be considered as the minimum summation, minimum aggregate thickness in a particular direction of force. So for us it will be 12, because in that direction it is 18 plus 8 plus 8, that is 16 mm. In this direction it is 12. So we'll be considering 12 and divided by 10 to the power 3 over here. So 270 into 17.5 into 12 divided by 1000. This will give us 56.7 kilonewton. So this is 56.7 kilonewton. So over here, answer is minimum of the two, and it is 43.29 as the answer. So that will be your rivet value. Now let's see this next question over here. In this next question, this figure is given to us, and in this figure there is a double cover butt joint, and double cover butt joint with the values of pitch and gauge values are given. So pitch and gauge are 50 and 50 over here, and the entire length of connection on one side is 150 mm. Now here in this question, please read this. A double cover riveted butt joint is given, and it is used to connect two flat plates of 200 mm width and 14 mm thickness as shown in the figure. There are 12 power driven rivets of 20 mm diameter at a pitch of 50 mm in both directions on either side of the plate. Two cover plates of 10 mm thickness are also used. The capacity of the joint shall be calculated in bearing and shear only. So here you are supposed to find out total shear strength and total bearing strength. So total shear strength and total bearing strength will be considering all the bolts together. Right? It's a double cover butt joint. It's a double cover butt joint. So it's a double cover butt joint over here, and you have to consider all the bolts together, right? And all the bolts together, and all the bolts will be also individually under double shear. So I'll be multiplying 2 for double shear. How many number of bolts are there on one side? 12 bolts are there. 12 multiplied by the permissible shear stress, that will be 100 MPa. It is given to us in the question. If you are not able to remember it, there's no issue. 100 multiplied by pi by 4 into d naught square. So over here d naught will be how much? 21.5. Again, it is less than 25 mm, therefore I'll add 1.5 to it. So it is pi by 4 into 21.5 square. So you can just directly find it out from this. So I can say 2 into 12 multiplied by 100 multiplied by pi by 4 into 21.5 square, and this will give us 871.32 kilonewton. Consecutively, you can find out PB as well. PB over here will be permissible bearing stress, and total number of bolts obviously we'll have to consider once again. So 12 multiplied by permissible bearing stress, that is 300, multiplied by d naught into t. D naught for us is how much? 21.5. Now, how much is the main plate thickness? Main plate thickness is given to us, two flat plates, 14 mm thickness are there, and cover plate thickness is 10 mm. So sum of cover plates is 20 and main plate is 14, so I'll be considering 14 over here, right? Get the answer. 12 into 300 into 21.5 into 14, right? And this will be 1083.6 kilonewton. Obviously the answer will be minimum of the two, so over here 871.32 shall be your answer. 871.32 will be your answer over here. Simple, two step. So I avoided all the things and just directly wrote down the numerical part. Next question. So for a field weld as shown in the figure of size 10 mm, they are saying that two plates are adjoined at a 99-degree angle. What will be the effective throat thickness? Now as per IS 800/2007, they have told us that the throat thickness is dependent upon the angle between the fusion faces, right? And when the angle between the fusion faces is, so throat thickness is how much? It is K times S. So this value of K is dependent between angle of fusion faces. So when we consider the angle between fusion faces from 60 to 90, the value of K is 0.7. When it is from 91 to 100, this value is 0.65. Just subtract 0.05 every time. 101 till 106, it is 0.6. From 107 till 113, it is 0.55. And from 114 till 120, it is 0.5. Right? So these are the values of K. So with respect to the figure which is given to us, 99, this is 0.65 we have to consider. 0.65 multiplied by S, right? So over here S is 10, so answer would be what? 6.5. This will be your final answer. As simple as that, no issue. Next, over here, so I'm very sorry. Yeah, so maximum size of a fillet weld for a plate is, so maximum size of a fillet weld is dependent upon the shape of the edge of the plate. If it is a square edge, it will be thickness minus 1.5, and if it is a rounded edge, it will be 3/4 times the thickness of the rounded edge. So over here there are two options which are giving us the maximum size of the fillet weld. Option A is giving us for the square edge, and option C is giving us answer for the rounded edge. Therefore over here our answer is A and C, right? So A and C is the correct answer over here. Let's see this next question. Over here this question is from welded connections, and it is a NAT question. Yeah, NAT question. So two plates are connected by fillet welds of size 10 mm thickness and subjected to tension as shown in the figure. The thickness of the plate of each plate is 12 mm. The yield stress is given 250 MPa, and also they have given to us FU value 410 respectively, and this is your connection. And over here you are supposed to find out the minimum length of the overlap on each side of the weld. So you are supposed to find out this value of L over here, so that it is able to transfer 270 kilonewton, which is a factored value of load over here. Okay, so minimum length which will be required will be consecutively with respect to 270 kilonewton. So I forgot to add the animation. I'm really sorry. So answer would be 105, but let's solve it first. So the total load which has been applied, let's say this is what 270 kilonewton. It has to be transferred to the weld, obviously, right? The weld will be taking this particular force, and the size of the weld is given to us as 10 mm, right? And when you consider that PdW, it will be equal to Fu divided by root of 3 divided by gamma mW into the length of weld into throat thickness. This is your formula for finding out how much design of weld. And over here this Fu is equal to 410 MPa and gamma mW is equal to 1.25, right? They must have given this in the question. So workshop weld it is 1.25. Length of weld over here will be equal to twice of L, and throat thickness will be equal to 0.7 times the size of weld. Size of weld is given to us as 10 mm. So 0.7 into 10. Substitute all the values, so you will get 270 into 10 to the power 3, which will be equal to 410 divided by root of 3 divided by 1.25 into 2 times L multiplied by 7. Right, so get the answer. 270 into 1000 into root 3 into 1.25 divided by 410 divided by 2 divided by 7. So answer is coming out as 101.84 mm on each side. So we have to round it off to an integer on the higher multiple of 5 mm. So answer is coming out as 101.84. So we have to just round it off to 105, which will be your correct answer. So please keep it in mind that whatever is written in the bracket while answering, the units, rounding off and everything, that turns out to be important with respect to the NAT questions, because the range is given to us and your answer should fall within the range. Now let's see this next question. Two plates of 8 mm thickness each are connected by a fillet weld of 6 mm thickness as shown in the figure. The permissible stress in the plate and of weld is 150 MPa and 110 MPa respectively. Assume the length of the weld shown in the figure to be effective length, the permissible load value of P. So the load which will be permissible on this particular connection shall be in such a way that both weld as well as the plate are safe. So both shall be safe, and then only you will have to consider that. So obviously I'll have to check consecutively whichever is the minimum value, that shall be your answer. So permissible stress in the plate, it is 150, right? So 150 multiplied by the area of the plate. So which plate will you consider? The smaller plate, smaller width plate, because obviously the width is less. It will be able to carry lesser value of load. So the strength will be calculated with respect to the lesser value of plate width. So 50 multiplied by thickness of the plate. Thickness of plate is given to us as 8 mm. And over here this 8 is nothing but a value 150 into 50 into 8 divided by 1000. This will give us 60 kilonewton. Now let's check the strength of the weld. In case of weld, it is a 6 mm weld. Permissible stress in the weld is 110 MPa. We'll multiply it with the area of the weld. So length of the weld is how much? 100 plus 100 plus 50. It will be 250 multiplied by throat thickness. 6 mm is the size. So 0.7 into 6. Let's do that. It will be how much? 110 into 250 into 0.7 times 6 divided by 1000. 115.5. So obviously the answer would be 60. Right? So for us the answer would be 60 kilonewton, the lesser of the two. Let's check this question out. So this question is containing this particular figure. In this particular figure, you are supposed to find out how much maximum shear force will the weld at the junction. It's a built up cross section, and built up cross section built out of a plate, a box section, and welding is done over here, over here, over here, and here as well. Right, and you are supposed to find out that how much maximum shear force will be taken up by the weld. Now while considering that, you will be considering the formula of shear stress. Where? Shear stress, which formula? The shear stress formula which you have studied in your strength of materials. At a particular point in a cross section, it is equal to VQ by I into V. That is the formula which you generally consider. Now here, this maximum shear force which is supposed to be taken up by the cross section, this is supposed to be calculated. And the maximum shear force should be in such a way that the weld should be safe. Right? Now, the moment of inertia of the entire cross section is given to us in the question itself, 7.73 into 10 to the power 6. The permissible shear stress in the weld is also given to us 100 MPa. Right? So here, this will be the value of tau, right? Because weld is to be taking, right? Weld has to take, what is this? Take this distance from where? From the neutral axis you have to take it, this distance. Total depth, within this it is how much? The total depth is how much? 120. And this thickness is how much? 10 mm. Right? So while calculating the value of Q, it is what? A into Y bar. So V is supposed to be found, and A is this area, 100 multiplied by 10 multiplied by this total distance is what? 60. 120 divided by 2. And this thickness is how much? 10. So we have to consider the CG of this area from the neutral axis. This will be what? 55 mm obviously, because 5 mm from the top you can subtract. So over here, take this as 55 as Y bar. Moment of inertia is given to us in the question, 7.73 into 10 to the power 6. And width, you will consider B value over here will be considered as the thickness of this weld, right? So this B over here will be equal to 4 times throat thickness. So over here this throat thickness will be equal to size of the weld is how much? 10 mm thick fillet welds is given to us. So 4 into 0.7 into 10 is given, right? So it is what? 7 4s are 28 mm. So width over here shall be considered as 28, and consecutively you can find out the value of shear force. 100 multiplied by 7.73 into 10 to the power 6 into 28 divided by 1000 divided by 55, right, divided by 1000. This will turn out as 393 as your final answer, right? 393.5 will be your final answer over here. Okay, let's see this next question. In this next question, it may seem that this particular question which is there, it was actually one MCQ question in gate examination for a moment-free connection in welded case in angle sections. But I have converted that into an NAT question, a simpler version of NAT question. Here you are supposed to find out a weld is used in joining an ISA of 100 by 100 by 10, which is shown in the figure. It has to be, connected on both the sides. Obviously the length N1 closer to the CG line will be of a larger length, and L2 will be of a longer length over here. Okay. As for the consideration, the permissible stress in an angle is 150 and that in the shear stress is 108. You are supposed to find out the ratio between the length L1 and L2, right? The position of CYY is mentioned 28.4 mm. Obviously this will be what? 100 minus 28.4. Now when we say that it is a moment-free connection, for a moment-free connection, the summation of the moments about any point would be equal to what? 0. So let's take that this was your CG line, right? So moment about CG line, when you consider equal to 0 summation of moments, this would give you L1 x1 equal to L2 x2. This would give you L1 x1 equal to L2 x2, where x1 is equal to the CYY and x2 is equal to this value, right? So here this L1 divided by L2 will be equal to x2 divided by x1. So here this x2 divided by x1 is nothing but 100 minus 28.4 divided by 28.4, that's it. So 100 minus 28.4 divided by 28.4. This will give you 2.52 as the answer over here. So this will be your answer, 2.52 over here. As simple as that. You can just remember this as well. It will be helpful for your future reference in various exams as well also. Let's see the next question over here. In this next question, they are saying in a fillet weld, the direct shear stress and bending tensile stress are given to us as 50 MPa and 150 MPa respectively. As per IS 800 2007, the equivalent stress. So as per IS 800, the equivalent stress is equal to under root of 3Q square plus FB square. So over here, this 3 into Q. Q is how much? Q is 50 plus 150 square. So 3 into 50 square plus 150 square, square root of this. This will give us as answer 173.2 MPa, right? 173.2 MPa is your answer. Let's see this next question over here. This is a question, again, this was an MCQ question, but this has been converted to NAT. Here, this eccentric connection is there, but to be precise, the value of moment is given, that only moment is there in this particular connection. There is no direct force. So this moment in this eccentric connection will induce only one shear force in each and every bolt which is there. And if you see that the CG of the connection is over here, the radial distance of each and every point will be how much? Half of this, that is 100 a half, 50, and 100 half 50, 50 and 50 over here. This will give us what? 50 root 2. So here radial distance, it is equal to 50 root 2 mm, and the value of F2 which get induced due to how much? Due to this particular moment m, it is nothing but m multiplied by the radial distance and summation of sigma of r square, right? Ri square. That means sum of square of radial distance of all the bolts. So here the moment is given to us as 50 kilonewton meter. So if I want the answer in kilonewton, I have to convert this in mm because all the other distances will be in mm. So 50 into 10 to the power 3, getting the answer in kilonewton mm over here, because all the radial distances will be in mm. 50 root 2 is in mm. So keep in mind the units as well, what units are being used in the numerical. So it is 50 root 2, that is your radial distance. And how many bolts are there? 4 bolts are there. So all have same radial distance. So 50 root 2 square multiplied by 4. Right. And this is what? 50 into 1000 into 50 into 2 root divided by 4 divided by 50 square divided by 2. This will give us 176.77 kilonewton as. Here in this question, a 16 mm thick gusset plate is connected to 12 mm thick flange plate of an I section using fillet welds on both the sides as shown in the figure. The gusset plate is subjected to a point load of 350 kilonewton acting at a distance of 100 mm from the flange plate. Now this is the consideration which has been shown. You need to find out the maximum resultant force which is acting in the fillet in the vertical over here. So here you can find out how much will be the direct stress, that will be your direct shear stress, and how much will be your bending stress, right? How much will be your bending stress? So direct stress Q will be nothing but the load divided by the weld area. Here the load is how much? 350 kilonewton into 10 to the power 3 divided by the weld area is how much? 500 divided by the throat thickness. The fillet weld is given to us as fillet weld is of 10 mm size. So 0.7 into 10, as it is on both the sides, so I'll multiply this by 2. So this will be what? 350 into 1000 divided by 500 divided by 0.7 into 10, 350 into 1000 divided by 500 divided by 7 divided by 2. It will be 50 ampere. And then getting the value of FB. FB over here will be equal to what? P times E. P times E, that is 350 into 100 divided by the moment of inertia, M by I multiplied by Y. So over here this P is 350 into 10 to the power 3 multiplied by eccentricity is 100 multiplied by Y over here will be how much? It will be 500 divided by 2, that will be 250 divided by moment of inertia of this entire weld area. 1 by 12 into B will be how much? Twice of throat thickness, so 2 into 0.7 into 10, so 7. That will be your B, and multiplied by 500 cube, right? So yeah, get this 350 multiplied by 1000 into 10 into 250 multiplied by 12 divided by 14 divided by 500 cube. You'll get 60 ampere. And equivalent stress will be required over here. 3Q square plus FP square. So 3 into 50 square plus 60 square. Over here 3 into 50 square plus 60 square. Getting it? This will be 105.35 MPa. This will be your final answer. Right. So yeah, this will be your final answer, 105.35 MPa over here. Now let's see this question. This was a question which was asked in this year's GATE examination. Now many people thought that this particular diagram which was given in this question, it is of a battened column, and many were not able to solve it as well. Even the renowned ones were not able to solve it. And as simple as that, if you have done good number of questions over the years, and specifically the design questions, if you will be doing in especially engineering services mains like examination questions, if you must have been knowing, then this question would have been very easy for you, right? This is the first time a very challenging question I saw in GATE examination from steel structures, because it was a part of design of connection in a battened column, right? And we, as we know that each batten which there in a battened column, battens are designed for longitudinal shear as well as a moment, right? And that longitudinal shear and moment will be transferred to the connection, and for that you'll be designing what? The connection of a battened column, of a batten specifically. Now what they had given to us in the question is that a built-up column was given and longitudinal shear as well as moment was there, okay? And now when we see, right, as per whatever design, whatever sign conventions you are considering, there will be a direct shear and there will be a moment in each connection. So if you are considering like this a diagram for the connection, this is nothing but the design of the connection will be same as that of a type 1 eccentric connection, right? Same concepts of F1, F2 and getting the resultant value will be considered in this question over here. So this is quite an easy question if you would have known the concepts, but nevertheless many good people were also not able to solve it, who aim to be good and who tell people they are good, but they were not able to solve it. Moreover, consider the built-up section over here, and there are 6 black bolts, and each connection of the batten plate with the component section is to be designed for a longitudinal shear 70 kilonewton and a moment of 10 kilonewton meter is there, and minimum bolt value is to be calculated over here, right? Minimum bolt value will be nothing but, as you all know, that the resultant force in each bolt, right, extreme bolts, that is your critical bolt in the connection, shall be less than equal to what? Bolt value, right? This is the consideration which is to be taken care of. Now, what they had given us, they had given us the value of F and M. So value of F1 will be equal to what? F divided by N, which will be equal to what is the longitudinal shear, that is 70 divided by 6. So over here 70 divided by 6 will be equal to 11.67 kilonewton, and F2 will be nothing but moment multiplied by radial distance divided by sigma of radial distance square, right? And let's say for this bolt, this bolt, this bolt and this bolt, obviously the radial distance will be same. Let's say it is R1, it will be equal to under root of 140 square. They have given the value of pitch over here, and